Hello, friends. Welcome to Science Talk. I am your host and resident oceanographer, Jim Massa. I came across this study that was published at the end of December 2021 in Geophysical Research Letters. And it's an interesting study because, here's the title of it: Zonal Structure of Tropical Pacific Surface Salinity Anomalies Affects ENSO Intensity and Asymmetry. And we can see that the authors are Kong Guan, Feng Tian, Michael McFadden, Fan Wang, Shijian Hu, Ronghua Zhang. And my apologies for butchering those names. But it just came out. Of course, I will leave the URL link in the comments section. And what they wanted to do was they wanted to look at how the surface salinity anomalies affect the ENSO cycle and the intensity of the different aspects of ENSO, be it the El Nino, La Nina, or the neutral in between conditions. So let's take a look at the abstract. Previous studies have revealed the potential importance of salinity in ENSO asymmetry, but the responsible mechanisms remain unclear. Here we investigate how the zonal structure of surface salinity anomalies affects ENSO intensity and asymmetry by modifying freshwater flux in general and ocean general circulation model simulations. Results show that the amplitudes of El Nino and La Nina are both highly sensitive to zonal patterns of salinity anomalies, with the strongest sea surface temperature change occurring when maximum salinity anomalies are located near 170 degrees west longitude. So when you have the maximum salinity anomalies, in other words, the greatest departure from average near 170 degrees west longitude, is where we see the strongest change in sea surface temperatures. Furthermore, the effect of salinity anomalies in the central Pacific on El Nino warming is larger than those in the western Pacific on La Nina cooling. Thus, the asymmetric salinity anomalies strengthen the temperature asymmetry between El Nino and La Nina. Temperature budget analysis shows that vertical mixing and entrainment due to salinity-induced changes in stratification are a major response to different zonal patterns of freshwater flux forcing. Okay, so let's take a quick look at the plain language summary. Salinity has been suggested to play active roles in the development of ENSO events by affecting vertical stratification. Recent studies found that maximum salinity anomalies are located in the central equatorial Pacific, henceforth abbreviated CEP, during El Nino, and in the western equatorial Pacific, henceforth abbreviated WEP, during La Nina. This pattern suggests a role for salinity in ENSO temperature asymmetry, but the underlying mechanisms are unclear. In this study, we conduct a series of sensitivity experiments to investigate salinity effect on ENSO intensity asymmetry using an ocean general circulation model. Results show that intensity of both El Nino and La Nina are highly sensitive to the zonal patterns of salinity anomalies in the tropical Pacific. Salinity anomalies have the largest impact on the development of ENSO events when they are located in the CEP, near 170 degrees west longitude. Therefore, salinity anomalies in the CEP contribute to stronger warming during El Nino, while those in the western equatorial Pacific, WEP, lead to relatively weaker cooling during La Nina, which strengthens the sea surface temperature asymmetry between El Nino and La Nina. Our experimental results further show that changes in vertical mixing and entrainment are a major factor in the temperature response to salinity anomalies. Okay, so let's see what they got going on here. Understanding the complexity of ENSO has been a long-standing issue and key to improving forecast model skill on seasonal to interannual timescales. Understanding the amplitude and spatial asymmetry and sea surface temperature between warm phase, El Nino, cold phase, La Nina, is challenging. This asymmetry with larger sea surface temperature anomalies during El Nino than during La Nina is manifest by a positive SST skewness in the eastern Pacific and a negative skewness in the western Pacific. Large number of previous studies focused on the role of air-sea coupling processes in modulating ENSO asymmetry. Freshwater flux, hereforth abbreviated FWF, and resultant sea surface salinity, SSS, exhibit large interannual variability in the equatorial Pacific. How these processes affect the ENSO asymmetry is pretty much unknown. In the western central tropical Pacific, the freshwater flux forcing and salinity act as a positive feedback effect on the sea surface temperature variability associated with ENSO. During El Nino, large positive freshwater fluxes, negative sea surface salinity anomalies enhance vertical stratification in the upper ocean. A thicker barrier layer appears between the mixed layer and isothermal layer, which warms the upper layer by reducing the subsurface entrainment of cold water and vertical mixing. That's kind of basically a way of saying that during El Nino, the pycnocline / thermocline is depressed. There's little vertical mixing, and there's no nutrients in the photic zone, and that's why productivity tends to drop off during El Nino events, and you kind of have the reverse situation during La Nina events. Based on coupled model analysis, Zhang et al. In 2012 found the freshwater effects can enhance cooling during La Nina and warming during El Nino, respectively, though changes in salinity and buoyancy flux that modulating the vertical mixing and entrainment in the upper ocean. Now, buoyancy flux is just another way of saying when similar densities find their layers in the ocean. In other words, if you have, say, more dense water at the surface and it starts sinking, it will sink until it comes to a layer that's more dense than it, and that layer, because of its buoyancy, will then, basically stop that layer that just been sinking at the new depth. That's basically what buoyancy is all about. Okay, so moving on here. Recent increases in salinity observations have made it possible to investigate the role of salinity in ENSO asymmetry. For example, based on 17-year Argo observational data set, Wan Hu et al. In 2019 found maximum salinity anomalies appear in the CEP during El Nino, while they are located further west in the WEP during La Nina. They suggested that different zonal locations of salinity anomalies may have an impact on ENSO temperature asymmetry through affecting vertical density stratification. However, while the asymmetric sea surface temp anomaly patterns during ENSO cycle is sensitive to the zonal pattern of salinity anomalies, how precisely this all affects is unclear. So they try to address that in this study. Okay, so then they go into a model and experimental design. Though, I'm not going to go through that. I will leave the URL link in the comments section for those who want to read it. And while I'm thinking about it, let me zoom down to this here. For those of you who click on the URL that I provide, you may want to click on this link here. It shows supplemental figures, which I will be referencing in this video presentation. It's basically it's a Word document. Okay, so I'll leave that there, and for those who want to look at those diagrams and figures, click on that link. Okay, back to where we were. Here we go. Okay. So what they did was to diagnose the salinity effects of ENSO, sea surface temperature. They simulated salinity anomalies by changing the strength and patterns of freshwater forcing. Freshwater forcing affects the ocean through modulating the upper layer salinity and the mixed layer depth due to buoyancy fluxes. And these fluxes have a direct and immediate impact on sea surface salinities on interannual timescales. For simplicity, we will interpret FW effects in terms of salinity responses in this study. So basically, it's like what's going on here with the freshwater fluxes. Okay, so the model had 20 vertical layers with varying sigma values. That's basically for salinity, and a mixed layer at the top determined by a mixed layer model. FWF, precipitation minus evaporation, is treated as a natural boundary condition. So basically, they're looking at the difference between precipitation and evaporation. If precipitation is greater than evaporation, you have a freshwater flux. You have it that is positive because you are adding fresh water. If it's the reverse, if the evaporation is greater than precipitation, your freshwater flux will be negative because you're losing the fresh water. So the freshwater flux is really looking at the difference between precipitation and evaporation, which is a major important aspect of what happens in tropical oceanic waters. You have a lot of evaporation due to the heating from the sun. The clouds build up and it rains. Well, where it rains is not necessarily right directly over where it evaporated, because you have things called wind, and the winds can move the clouds around. The atmospheric cells that can move the clouds around, etc. So they look at that. And when you consider the traditional view explanations for ENSO, typically it's like there's a low pressure system over in the Indonesian area, and when it moves west and east, will determine what the sea surface temperatures are, if the pycnocline / thermocline gets depressed or not, and whether or not you get warmer sea surface temperature. It was always kind of placed in those terms. Well, now finally look at what the salinity effects are. So I'm sure there'll be folks who will find plenty to criticize or suggestions for improvements in future studies. But hey, this is a start, and it's a continuation of recent research efforts. And it's other aspects of model configuration described in the supplementary material. That's the Word document I just referenced. They got wind stress data from the CEP NCAR reanalysis. They're monthly from January 79 through December 2016. Basically, they they looked at to diagnose the salinity effect. They simulate salinity anomalies by changing the strength and patterns of freshwater flux forcing, how much rain, precipitation, evaporation, and where it takes place. That's basically what they did. And they did sensitivity studies. Let me take you right to figure one, the description figure one, and then we'll highlight this. Sea surface temperature anomalies are shaded during the mature phase, December through February of El Nino. And that would be A through C. That's this top row here. You see right there, El Nino, La Nina, and then the asymmetry. Okay. La Nina, D through F, the middle row, and their differences, the asymmetry, G through I in tropical Pacific. Sea surface temperature anomalies forced only by the interannual wind stress anomalies are shown in the left panel, basically the left column. Sea surface temperature anomalies forced by both interannual wind stress and twice observed freshwater flux anomalies are shown in the middle panel. That's this. So it's the middle column. And then the last column, sea surface temperature anomalies with sea surface salinity anomalies overlaid induced by freshwater effects. Basically, the left minus the middle are shown in the right. The unit for SST is degrees Celsius. For freshwater flux, it's millimeters per day. And for sea surface salinity, PSU, which practical salinity units. Well, let's enlarge this here a little bit. Okay. So again, this is El Nino, this row here. This row is La Nina. This row is the asymmetry. Notice the difference. So when we look at just wind forcing, we see that the temperature anomalies, it's warmer on the eastern side of the tropical Pacific. That's basically what we have here. Okay, and so here is longitude, and they're saying 170 west. So that basically, when they find the most results, 170 west, it's pretty much like right here. So that's just looking at just wind stress. Now, when you look at wind stress and freshwater fluxes, we see basically similar patterns here. Okay? We see some similar patterns. Okay? And the contour lines represent the changes in the salinity. And now when they look at the salinity minus effect, in other words, you can see right here, B minus A. Okay, so B is wind plus freshwater flux minus A. So this here is basically just looking at only the freshwater flux influence. It's subtracting out the wind contribution. And what do we see here? We do see a further movement in the temperatures to the west. We see that. And in fact, it appears to be even more expansive, the warming. Okay? So these are showing temperature anomalies, is what they're showing. Now, look at La Nina. We see similar results with just the wind and wind plus freshwater fluxes. Similar result. The ocean water is cooler by up to 1.5 degrees C less. And we can see it's up to 1.5 C warmer during El Nino. And then when we subtract out the wind component, you can see what? That the cooling appears to also move a little bit towards the west as well. And now look at the asymmetry. Now, when you look at the asymmetry, what they're really doing is taking into account both of these. They're adding them and then see basically which anomaly is greater. So, for example, when you see this cooler spot here, okay, if you add that and add that, yeah, that makes sense. You're going to get cooler temperatures. But now look at this here in the middle. We have very, very warm. So we add this very, very cool. But overall, it's a little warmer. It's not as warm, of course, but it still is warmer. So that's kind of how you look at these guys here. And, looking at the wind and the fresh water, okay, we see a similar response. It looks pretty much the same as it does here. Where it gets really interesting is taking out the wind component and, well, no surprises here. It's kind of warm here. The warmer is greater than the cooling anomaly, so we're left with a net warming situation. And what's interesting to note is that in all these three cases here, the western equatorial Pacific is cooler. That's the thing. That's the one take-home message out of this. So at least they're trying to account for the effects of salinity. Now I will pull up the supplementary figures later on to further discuss and highlight some of the findings. During both El Nino and La Nina, freshwater flux anomalies start in July with 3 millimeters per day, gradually increasing to a maximum exceeding 9 millimeters per day in winter, weekend, and spring. During the mature phase, is shown that the maximum freshwater flux anomalies appear in the central equatorial Pacific, which is defined here as 170 degrees east to 150 degrees west longitude, 5 south to 5 north latitude during El Nino, and the western equatorial Pacific, 120 east to 170 east longitude, and 5 south to 5 north latitude. So we've got the same latitudes, but you'll notice a bit of a shift. 120 to 170, so that's 50 degrees longitude being covered there. 120 to 150 west, that would be 40 degrees of longitude being covered there. So it basically, if you look at this here, the transition point is at 170 degrees east longitude. Under these freshwater flux forcing scenarios, sea surface salinity anomalies during El Nino appear in the CEP with a maxima exceeding 0.2 practical salinity units, leading to enhanced surface warming of 0.2 C. During La Nina, the sea surface salinity anomalies occur in the WEP with maximum more than 0.1 PSU, accompanied by extra cooling of up to minus 0.2 C. As for the asymmetric features between El Nino and La Nina, sea surface salinity anomalies present a dipole structure as seen from the Argo analyses. More importantly, the salinity-induced sea surface temperature anomalies also exhibit a dipole pattern in the western central Pacific within 10 degrees east to 10 degrees north, with a negative pole west of the dateline and a positive pole in the central Pacific. That's basically, that's this right here. That's what they're talking about right there. There's your dipole. That's what they're getting at. These results preliminarily reveal that freshwater flux and salinity can enhance the intensity asymmetry of ENSO sea surface temp and so forth. Okay, so the sensitivity of ENSO sea surface temperature intensity to sea surface salinity anomaly, and based on the longitude. And here they mention a freshwater flux window is set to span 40 degrees in longitude within the 5 south to 5 north or 10 degrees of latitude. And then they say, according to magnitudes and evolutions of the twice freshwater flux composite, freshwater flux intensity in El Nino is increased gradually from July, September to November of the first year as 3, 6 to 9 millimeters per day, then decrease symmetrically from March, May to July of the next year. During La Nina, the same evolution but with negative magnitudes. So I'm just going to go right to figure 2. Freshwater flux sliding window, A, okay, we'll show that in a bit, and the 4 sea surface temperatures anomalies, thick black line, during the mature phases and temperature budget terms, represented by various color lines here, during the developing phases of El Nino B and La Nina C. The x-coordinates of B and C are central longitudes of the freshwater flux forcing. Okay, so let's take a look at it. Well, here's the positive freshwater fluxes here, and these are the negative freshwater fluxes there. But what I really want to point out to you is here's the El Nino. So here's the sea surface temperature anomalies. So this is positive, this is negative. Okay? And what do we see here? It pretty much looks symmetrical for the most part. Symmetrical. And you can see what? Right there. See the high point there? That's right on 170. Right there. So what are these other color lines? Well, the cyan is the vertical mixing and entrainment. Then we have the purple is meridional advection. So that's moving longitudinally. The gray is the sea surface temperature tendency. So this is like a departure from the tendency. Then we have the Q net, which is Q is probably for heat. And let's see what else we have. Zonal advection is in, what is that, orange? Yellowish? Whatever that color is. Ladies can determine the colors differentiation better. They have more cones in their eyes, so they can differentiate colors better than men can. So, ladies, if you ask your significant other about colors and he says, I don't see a difference, do not get angry. They really can't. And then what do we see for the La Nina situation? Once again, the lowest temperature deviation is at 170. But if you were to look at these figures and the different aspects represented here, and my focus is concentrating on the temperature. But if you were to look at this here, it's like you took this graph here and you simply rotated it, over a horizontal axis, like you rotated over the 0 line to get this. Right? Look at the temp. It's almost like a mirror flip. And recall in the text, they talked about departure of up to 0.2. Here they're showing 0.15, and we see the departure down is minus 0.2. So it's almost like you just totally flipped this over, like a major oscillation. That's the importance of what this graphic is showing. With anomalous freshwater flux forcing, the WEP becomes immediately fresher during El Nino and saltier during La Nina. That's figures S2 to S5. The surface anomalies, salinity anomalies, are found to have similar amplitude and shift eastward along with the freshwater flux window in either El Nino or La Nina event. In response to the freshwater forcing and the effects of salinity, sea surface temperature exhibit a different evolution depending on the zonal location of where the fluxes are and where the salinity anomalies are, with its strongest responses in the CEP. Salinity-induced sea surface temperature anomalies average in the Nino 4 region, and they give you the coordinates there, during the mature phases of El Nino and La Nina, as shown in figures 2B and C. Here, we can just look at the values and look at where they correspond longitudinally. And they go on to give further descriptions. Then now they talk about the heat budgets. That's getting a reference to the QNet graph that we saw. And let's see. So what are some of the more interesting things here? The sea surface tendencies are positive in all the experiments, indicating salinity anomalies in all the locations can produce warming effects on the development phase of El Nino. The change in vertical mixing and entrainment is prominently positive, with its peak of more than 0.15 C per month. Right, month minus once per month, near the date line, which is largely dampened by the negative surface net heat flux. Meridional advection is weakly positive. Zonal advection is weakly negative in the Central Pacific, whereas vertical advection is very small. During La Nina, the sea surface temperature tendency is generally negative in response to salinity anomalies at all locations, becoming stronger to the east. The change in vertical mixing and entrainment is negative and contributes most in the Western Central Pacific. The surface net heat flux is weakly positive in the Western Pacific, tends to be negative east to the date line. In summary, okay, for both El Nino and La Nina, the dominant oceanic process that results in the sea surface temperature response to the zonal location of the surface salinity anomalies is vertical mixing and entrainment, which contributes most remarkably in the CEP to the development of ENSO sea surface temperature anomalies. So there's your summary right there. Compared to other parts of the equatorial Pacific, Salinity anomalies in the CEP will be most effective under stratification stability and hence the ENSO SST. What they're basically saying is don't just look at the wind and sea surface temperature for ENSO, but look how salinity and changes in freshwater fluxes affects the formation. In other words, this is an important aspect in what drives the ENSO cycle. It's not just wind and sea surface temperature, it's also salinity, but more importantly, how the freshwater input or removal affects everything. All right, as discussed earlier, surface salinity anomalies in the Central Pacific can result in stronger surface temperature anomalies during both El Nino La Nina than those in the Western Pacific. So now they just want to jump down to Figure 3. Figure 3 shows the evolution of this salinity and temperature anomalies in response to the CEP and WEP freshwater flux forcing, respectively. During El Nino, positive salinity anomalies are generated in the central equatorial Pacific, negative anomalies in the west. Affected by the positive salinity anomaly, clear warming occurs in the Central Pacific and subsequently reaches its peak in the El Nino mature phase. It is noted that maximum positive temperature anomalies are found more eastward by up to 10 degrees longitudes in the CEP case than the WEP case, resulting in a clear dipole structure as indicated by a difference, Figure 3C. We'll get to that in a moment. In addition, the CEP case SST anomalies have a larger amplitude, indicating that the CEP location of salinity anomalies favors stronger El Nino warming. And by the way, there's some indications that the way, because the oceans are warming up and so forth, that we could be pushing things eventually into almost kind of a permanent El Nino state of ENSO. That remains to be seen. During La Nina, most of the surface equatorial Pacific becomes saltier due to negative freshwater flux anomalies, i.e., more evaporation, except for the far western Pacific, resulting in cooling broadly along the equatorial Pacific and warming in the far west in both cases. So let's take a look, and again, they refer to a dipole structure. Let's take a look at Figure 3. Sea surface salinity anomalies, the lines, sea surface temperatures are shaded. During El Nino, A and B, La Nina, C and D in the equatorial Pacific, forced by the types of freshwater fluxes. So, wait for it to load up. Come on. Oh, it's taking so long. Okay. So, top panel, top rows, El Nino, bottom rows, La Nina. And here we're going from month, April, July, October, January, April, right? So this is over a year or so. And here is your longitudes. So the dotted lines are your salinities. The shading is your temperatures. And as you can see here, okay, CEP case, Central Equatorial Pacific, Western Equatorial Pacific case, and then the difference between the two. And as you can see in the CEP and WEP during El Nino, they're pretty similar. Pretty similar in the temperature, but the salinity slightly differs. Take a look at this isohaline line right here. See a little of that? Let me see if I can. Yeah, there we go. Okay, see that? We have this right there. And that departure is a 0.1 PSU difference, 0.2 minus 0.2 difference there, and a 0.3 difference there. right? So we got minus 0.1, minus 0.2, minus 0.3 difference in the PSUs. Those are the anomalies. And you can see that the stronger the anomaly, the warmer the temperatures are. But notice over here how the 0.1, the minus 0.1 isohaline uh, it moves considerably westward. See how it goes all the way over to 90 west? We're close to it, more like 100 west. And here it shrinks quite considerably. It moves considerably westward. And then when we look at taking the difference of the two, we get a couple of bands of the minus 0.05, just a little isolated 0.1, which makes sense. I mean, if you've got a 0.2 minus 0.15, you're left with 0.05. And you see that even though it's warmer, the warming is not as pronounced. In other words, the temperature anomaly. Let's take a look now for the La Nina situation. In the La Nina situation, we see colder waters. Okay, here's your 0.1 isohaline. Also over here, 0.2. No, really 0.3. And these values are positive. So it is saltier. Okay. Up here, the negative tells us it's fresher water. Here we have saltier water. So here it's more likely that precipitation exceeds evaporation. Here, evaporation exceeds precipitation. So we see similar things here. This is the CEP. This is the WEP. Very similar looking results here. And then when you take the difference, we suddenly get this warming trend here. And you notice now we've introduced extra fresh water. There's a slight decline in salinity. So that's basically part of what they're getting at in the text there. So now, let's look at figure 4. Sea surface temperature anomalies forced by the CEP and the WEP, FWF, cases during the mature phases of El Nino La Nina in the equatorial Pacific are shown in A and B. Temperature budget terms averaged in the Nino 4 regions during the developmental phases of El Nino La Nina are shown in C and D. Asymmetric sea surface salinity anomalies are in line, and then SST anomalies are shaded. And those differences are shown in E and F for the WEP. So let's take a look at this. Okay, let's see if I can enhance this a bit. So here are our departures. That's a warmer departure, cooler departure. Mature phase is the shaded region right here. CEP is central. WP is western. And you can see how it's warmest. The highest temperature departure occurs basically in this range of longitude right there. Now, when you look at the La Nina mature phase, you see how it's basically almost a flip of this, right? Here we go up to positive, an increased temperature of 0.15 C, and here we're having basically at its maximum negative departures, it's about minus 0.18 in the CEP case, less for the WEP case. But it's a flip. Warmer waters, cooler waters. Let's look during the development phase. And again, they're keeping the colors consistent here. So here's the heat, the net heat, zonal advection, meridional advection, vertical advection, and then vertical mixing and entrainment, and sea surface temperatures here. So in the developing phase, of course, it's warmer here. We see, and then SST's tendency is degrees centigrade per month. So vertical mixing and enhancing, basically it warms up, telling us that there's less vertical mixing. Here we see that it's negative, there's more vertical mixing. Temperatures are cooler. And then finally the CEP case and the WEP case, the asymmetry of it. And so here are our latitudes, here are our longitudes. The lines are the salinities, and the shading are the temperatures. Here's Central America. So there you can just see the coast of South America there. And you can see less cooler here, stronger cooling here. But it looks like a little more warmer in the central versus here. A little summation. Study examined effects of freshwater flux, sea surface salinity on ENSO intensity. We find that both the El Nino and La Nina sea surface temperature anomalies are highly sensitive to the zonal patterns of freshwater flux and salinity. And going back to this figure here, let's see if I can increase that. We can see, if you look at the zonal, let's look at say 10 north. We see more warmer water here than here. Look at the equator. It's cooler, but definitely a stronger, cooler response. You look at 10 south, might be a little warmer on the western side. And then, of course, you can see some of the difference at the 5 south and 5 north latitudes there. So that's what they're getting at with that statement. The salinity effects are strongest when the maximum salinity anomalies occur near 170 degrees, leading to an extra warming of 0.15 C during El Nino and extra cooling of minus 0.2 during La Nina in the Central Pacific. So what I want to do now is pull up those extra diagrams. Okay, first a little table here. Table S1, S for supplementary. Detailed experimental designs for the 2-year El Nino La Nina events. Experiment 1, construct ENSO events. So this column here is the control, and then these are the sensitivity experiments and the experimental objectives. So climatological annual cycles for the ocean state, wind stress, and freshwater fluxes. Control experiment plus El Nino, La Nina composite wind stress anomalies. And we want to test the ENSO sea surface temperature asymmetric features. And then they do the strength test on the freshwater flux. Climatological annual cycles of the ocean state, freshwater, and El Nino, La Nina composite wind stress. And the alpha 1, 2, 3 is referring to the intensity of the freshwater flux. So test the freshwater flux strength to reproduce sea surface salinity anomalies that are close to the observations. So like everything else, when your model can reproduce what is observed, you got a good model. Then you can, once you have that established, then you can sit there and say, okay, what if we have this? What would happen if this scenario? What are the likely outcomes under this other scenario, etc.? And they go on to describe what they're doing. Figure S1. Interannual freshwater flux anomalies in equatorial Pacific during El Nino on the top row and La Nina on the bottom row. And they're induced anomalies of sea surface salinity lines. That's these guys here. And the shading. For example, in E, where's E? There's E. 3x means put 3 times the freshwater flux anomalies. In other words, you have 3 times the precipitation, for example, or 3 times the evaporation. I think these. So yeah, you can see the shading here with the showing the temperature anomaly. So there's your greatest warming is near that 170 longitude feature. And yeah, and the 1, 2, 3, I think it looks like it refers to 1 times the flux, 2 times the flux, 3 times the flux, and how it responds to that. And then we see for each specific case what happens. These lines look like the salinity increased by zero point 0.1 PSU, zero point 0.2, and so on, and 0.2 and 0.3 here. And it's interesting showing that we get a little bit of cooling. And if you look at La Nina, again, overall, there's a little bit of cooling under the 1, 2, and 3 times the fluxing. And you see what? Then we get a little bit of warming. So there's that dipole. There's that switching that they talk about. Now, figure S2. Sea surface salinity anomalies in the equatorial Pacific during El Nino, corresponding to figure 2b. And the bluer means that it's getting fresher. And you can see how it changes, where it's, how it moves longitudinally. And then we see something similar. So this is during El Nino. That's surface anomalies for salinity, and then sea surface temperature anomalies in the equatorial Pacific during El Nino. And again, you can see warming situations. Then we come to sea surface salinity anomalies during La Nina. So the blue means it's getting fresher. So we got, so the figure S2 is showing sea surface salinity anomalies during El Nino. The bluer it is, the fresher it is, right? Because this means that the salinity has decreased, so we have fresh water, more precipitation entering the system. And they're showing it for each longitudinal band. That's what they're showing here. And then we look at, again, for each longitudinal band, we look at the temperature, and we see the temperature is increasing. Then they do the same thing during La Nina. And La Nina, okay, the red, brown, whatever it is, indicates that the salinity is increasing. So basically, you got more evaporation, less precipitation. And we see, for each longitudinal band, what those results are. And then we look at the temperature during La Nina, and we see overall it's cooler. So basically, what they're showing is that during El Nino, there's more precipitation. Precipitation exceeds evaporation, and then the temperatures are warmer. Whereas La Nina, there's more evaporation than precipitation, and the temperatures are cooler. So basically, El Nino has increased precipitation and increased temperature. It's the flip for La Nina. Decrease precipitation, or you can say increase evaporation, and decrease temperatures. And then finally, not finally, but the two cases of freshwater flux anomalies in experiments during El Nino, AB, La Nina, CD, CEP, WEP case, and again, warmer temperatures corresponding to a more precipitations. Cooler temperatures corresponding to more evaporation. And then finally, this is important here. Schematic diagram illustrating the effects of different zonal patterns of sea surface salinity anomalies on ENSO temperature, intensity, and asymmetry. And I'm going to bounce them back and forth. So El Nino, there's negative freshwater flux, sea surface salinity anomalies in the CEP. It's positive during La Nina. Salinity effects on the vertical stratification in the Central Pacific is greater than the Western Pacific. Increased vertical stratification, ML means mixed layer. The mixed layer becomes shallower and less stable, decreased vertical temperature gradient under the mixed layer. In La Nina, decreased vertical stratification, the mixed layer becomes deeper and more stable, increased vertical temperature gradient under the mixed layer. So in other words, because the mixed layer is deeper, you can bring nutrients into the photic zone and you get more productivity. When the mixed layer is shallower, you can't get that mixing. And then productivity drops off. And that's what they're getting here. So this leads to decreased vertical mixing and entrainment at the base of the mixed layer, increased vertical mixing and entrainment at the base of the mixed layer. Entrainment means trapping of nutrients and stuff like that. This leads to enhanced sea surface temperature warming that strengthens El Nino. This leads to enhanced sea surface temperature cooling that strengthens La Nina. And when take out the salinity minus the effect of the sea surface temperature, this leads to El Nino will be greater than La Nina. And that is kind of leading to what was basically, as mentioned earlier, that there's some indication that the equatorial Pacific could be heading almost to a permanent El Nino state of the ENSO cycle. That, of course, remains to be seen. Now, want to stress here, the negative freshwater flux is in the CEP, allowing for the warmer temperature. The positive freshwater flux is in the WEP, the western. We're still, as we just showed, we're having more precipitation in the WEP during El Nino. There's that dipole that's been mentioned back and forth. So to try and again, you can find these by clicking on that link. So basically, what they are shown here is that we need to account for salinity, the effects of salinity, and how the intensity of the ENSO events, where they're centered, and note the transition as we go longitudinally across the equatorial Pacific. So it's not just wind, it's not just temperature, but it's salinity, and tied into salinity is the evaporation precipitation cycles. That's basically what they're showing, that is an important factor in what drives ENSO, what drives the intensity, where the intensity is located, how where it's found. You could have different conditions in the western versus the central versus the eastern. That's what they're all showing. Now, granted, this is a modeling based on some observations, and the Argo data set. So this is new. Basically, it's recent research in the last several years, and it'll be interesting to see what their further research brings to us. So I found this interesting. I find this to be another piece of the puzzle in understanding ENSO, which of course helps us then understand climate for the planet. So I thank you for your time, and we'll talk soon. Hello folks, this is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.